Okay, so we're going to see another example now of a class. And this example is actually going to combine object-oriented programming classes in C++ with pointers. And one of the best examples to show where pointers and classes actually can work really well together is creating what are called data structures, which are things that store data and can grow dynamically, typically, that kind of thing. So things like linked lists, queues, and stacks. So we're going to look at today an example of a stack, because I know for those of you, for all of the people in the class here, in the other course that you're doing, the 1030, you've already spent a little bit of time learning what a stack is. So a stack is a data structure which is called a first in, last out, meaning that items get added into the stack. Think about like a tray, a stack of trays at a restaurant, right? The first tray that's put in the stack is the last one somebody takes out to use. So you just take from the top, you add to the top. So in order to do this, what we're going to do is we need some way of actually representing the items that are in our stack. And we're going to call these nodes. And so in order to do this, we're going to actually create a node struct. So we're going to use what we learned before about structs to create an item which will go into our stack. And we're going to call this a node. So we're going to create a struct called node. And what do you think node should contain? It could contain data, right? So do you want to have it contain an int, a string, what? String? Sure. String data. Okay? Sound good? Yeah? No? Now, the other thing that's interesting is that the node will also contain a pointer to another node. This is where it gets a little fuzzy because, remember, the idea of the stack, a stack itself is going to be the class. But what we want to do is we want to add a node. And then what we want to do is when we add an additional node, we want to know what node is above or below it and so on, right? So in our case, we want to know what node is below. Does that make sense? So we're going to chain these together in a way so that nodes will actually, one node will point to the next one in the stack, the next one, and so on. So we're going to dynamically be adding these. So that's the data structure we're going to use. Now, of course, this is just something which is really a helper structure that we're going to use when we create our stack. So unlike, a lot of you have done Java already, right? And you may have seen a stack in Java. And the thing about in Java is you just create new objects. But you don't actually use pointers, right? Because memory allocation would be done, is actually done, is done automatically, right? That you have automatic garbage collection and so on. Because in C++ with dynamic memory, we actually allocate and deallocate the memory ourselves. That's why we need to create a pointer here in this struct. So we're going to create a class called stack. And there's going to be things that are going to be private in here, and there are going to be things that are going to be public. Now remember, private means it can only be accessed within the class. Public means it can't. So in a stack, what do you think you would actually need as private data? Do you ever access the bottom of the stack? No. What do you always access? The top. So it turns out what we're going to do is we're going to have as our only private item right now is going to be a node, which is going to be a pointer to the top of our stack. So this is going to be a pointer which points to whatever item is at the very top of the stack. And we don't want anybody using our stack class, we don't want them manipulating the items in the stack. So we're going to make this private. Okay? So the only thing we're keeping track of is where the top of the stack is. All the rest of the elements in the stack and their relationship, whether one's on top of the other or if they're at the bottom, is all going to be kept track of using the next pointer. So we'll have a pointer to the top of the stack, and then we'll have pointers to all the other items. Okay? So that is the only data item we'll need. Now, we're going to need a couple things here. One thing we're going to need is we're going to need a constructor. And the constructor is actually what we're going to use to initialize our stack, meaning to set up the initial stack. Now, how many items should be in the stack when we start, probably? 0, right. So we're going to want our constructor to be used to set up an empty stack for us. Now, the other thing we're going to need is, because we're using pointers inside of this class, guess what we're going to need to do when we finish using this class? We're going to need something that's going to go through and properly delete all of the pointers, which is similar to what was asked earlier. So we're going to need to actually, when we have a class with pointers built in, we actually use this little tilde symbol and stack, and this is actually what's called what? Deconstructor or destructor, right? What do you prefer to call it? Okay. So what this is going to do is, this is going to go in and clean up all the mess we create in dynamic memory, i.e. clean up all of the pointers that we create. Okay. Awesome. Now, what other functions are we going to need here? Do you want to implement these first? Yes, thank you. We're also going to need 2 functions here, because we're going to need to be able to add items to the stack, and we're going to be able to remove items from the stack. Adding to a stack is called push. Removing from the stack is called popping, or pop off the top of the stack. So the push, what would be the way we would write this? Would it return anything? No. So it would go void push int, or actually no, we have string, right? String D for data. And this is going to pushes a node onto top of stack, okay? We're also going to want to have a pop, which is going to return a string. And we don't have to give any parameters, because by default, what string will be popped first? Top. So what this is going to do is, this will pop the top node off of the stack. Okay? Basically, those are the big, top 4 functions we need. There are some other ones we may add later, and I know I'm going to want to add later, but rather than go through and create a big complicated class, I'm going to start with the core functions first. That's typically how I would build a class. What's the core functionality first? And as we need additional functions, then we'll add them. Right? And some functions we may want to allow the user to use when they're creating a stack object. Those will be public. Some of them may be helper functions that we will actually only use ourselves internally. And those will be private. Okay. So let's go about actually creating some of these the functions. So for our constructor, remember, all of our functions that we define in our class have to be resolved back to the class. So we have to say stack colon, which means stack and the scope resolution operator. So by doing this here, we're actually saying the constructor resolves back to the stack class. And what we're going to do in this is, excuse me, we're going to initialize the stack to be empty. How do we initialize the stack to be empty? Well, the stack is empty if the top of the stack points where? Nowhere, right? If the top doesn't point to any actual location in memory, then it will be empty. So we do this by saying top equals null, which is the null pointer. So we say the top doesn't point anywhere yet. It's an empty pointer. Yes?
So the keyword null pointer is just like a reserved word for null?
Yes. Null here in this case, we're going to use the keyword null to actually indicate that this pointer points to no address right now, no memory address. Okay, so that's how our constructor works. And the cool thing now is that down in our main function, we could actually go about creating a stack. It won't be a very useful stack, but we can now create a stack. Let's call it S, and we're going to create it using new stack. What this is now going to do is it's now going to create a object of the stack class, which has what? It has a variable called top, a pointer which points to nothing. So it creates an empty stack. Awesome. Now, The problem, though, is what happens when we delete S? Right now, when we call delete S, it'll just delete this pointer here, right? But it doesn't actually do anything else. But if we actually implement our deconstructor, it will go ahead and automatically delete everything else we need. So we need to go and we also need to delete things here. Now, it turns out the only difference between the constructor and deconstructor in terms of the format is simply that little tilde right there. And in our case, how are we going to actually delete things? Yeah, so I'm gonna leave it blank right now. Okay, because we're going to want to delete stuff, but I'm going to just put out, just so you can see that this actually works. I'm going to put a little message here which says delete should be happening now. Okay? And this is way that you'll be able to see, once we actually implement our push and pop, you'll be able to see when the delete actually happens. Because we don't actually call a deconstructor, do we? In the normal sense? So because we don't necessarily call it, it's done when we do the delete. This way, we'll actually know it's actually working. And I'm only putting this in as a little test line, just so that you guys know your deconstructor has actually been running. So that's just something I'm just putting in here, but we're going to come back to this, okay? Now, what about this push and pop? Well, we need to implement these as well, right? So the push we had here, void. Now we need to say it's part of the stack class, push, a string. We're going to need this function to actually push something onto the stack. We're also going to need to have a string stack pop, which is going to pop off something off the stack and return a string. I'm just going to put in here now return empty, which is a string, right? These are not implemented yet. You can think of these as just placeholder functions or just the template. The functions are there, but they don't do anything, do they? So I've just got these empty functions here now because I want to make sure that my constructor works before I actually go about doing the push and the pop. Okay? So what I'm going to do actually, instead of delete should be happening now, I'm going to put a little if statement here, which just says if top equals null, I'm just going to say nothing to clean up. Otherwise, I'm going to say delete should be happening now. Okay? This is just a little if statement here. This is not the way the class will end up looking, but it's just a way for us to see what's going on. So basically, we set the top equal to null here, which means that we actually have not initialized. In the constructor, we haven't actually initialized or created any dynamic variables, have we? Right. So if the top is still null at the beginning, at the end of our use of the stack, what does that mean? We don't have to do anything, right? We don't have to delete anything because the top is not, there's no dynamic variable there. So let's actually just go about seeing, okay, when we create a stack and we delete it, does it actually detect that in fact it is empty? So what should be displayed when we create a stack, don't do anything with it and just delete it? What should we see as output? What? Yeah, we should see that message, nothing to clean up. So let's actually give this a try. I'll save the program and let's actually run it. Let's compile it first. See if it will compile. Oh, I've already got an error. Guess what I forgot to put? Semicolon after my class. So you have to remember a semicolon after after you define a struct or after you declare a class. So let's try this again. Compile. So let's run this. And it says nothing to clean up. That's awesome, because now we know our constructor worked, right? And we also know that our deconstructor is actually getting called as we expect it to. Okay? Not a very useful stack yet, but we know that those parts of the code work. And one of the most important things when you're building classes, when you're writing classes is sometimes, and it depends on your expertise and so on, but when you're first starting out with these things, if you just go and implement all the functions and then try to run them and they don't work, you're like, what's wrong, right? You have all the code to work out. And especially in a test situation, if you actually were having to implement a stack as part of your test or in a time-based lab, one of the big challenges is if you implement everything, trying to find where the problem is, you don't want to waste time. So what I like to do is I like to, as I'm building each function, make sure that function works before I actually go and implement something else. So what I'm going to do is I'm actually going to, does it make sense now to actually implement the push or the pop first? Push, why? Pop has to have data in order to be able to work. So what I'm going to do next is I'm going to implement the push function, make sure it works, and then I'm going to implement the pop function, make sure it works. And then I'm going to implement the deconstructor. Sound good? You're happy? Is everybody following? Am I going too fast, too slow? Okay. What? Yeah, it's mostly new examples, new code. So let's actually look at how we're going to implement the stack push. Well, this will be interesting. What are we going to do here? We will. So, but what we're going to want to do is for every item we want to push, what do we need to create for it? A node. So the first thing I would do when I'm pushing is we need a new node to store data, D in, right? To store D in. So the first thing I would do is I would create a node called temp equal to a new node. What is this going to do for me? It's going to allocate a dynamic variable. So it's going to allocate memory in the heap, which will have space for a data string and space for a pointer. Make sense? What? It doesn't matter because I'm just creating that temp. I'm just giving it a name. I'm going to create the node first, then I'm going to put it into the stack. Okay? So you can think about this as like an assembly process. First thing I'm going to do is I'm going to build the data, the node, then I'm going to add it to the stack. Okay? So that's the process that I would follow. Michael?
Just back up in our struct, like, why don't we have to do like node, and then when we're using our pointer, why don't we do like new, and then pointing to something like new string?
Because the struct only contains the data, the variables. It doesn't do any functionality. So what we do here is we create a pointer called next, and we do nothing with it. The expectation is once somebody creates a new variable, a new node variable, they will set up the data themselves. We also didn't initialize the data string to be empty or to be a default value, right? Setting up defaults like in a constructor is part of functionality. Structs don't typically contain that, right? So we'll see how that works now. Yeah?
Do you like call the node within the struct? You have a struct node and then you can call node pointer.
Yeah?
Why does that work?
In some ways that's recursive, right?
Yeah.
We have a node that contains a pointer to another node that contains a pointer to another node.
So that's what is making the stack then, I guess?
Yes. Exactly. The linking of one node's next pointer to a different node, to a different node, to a different node, that's the stack. So the stack is actually built by linking together the pointers. And I'll draw a diagram on the board and post it on the website after. So once we write the code, I'll walk through the code on the board so you can see how it gets created. But we don't actually go and create a stack, like an array, and start putting stuff in the elements. The structure is actually created by linking together the pointers. Okay, so we've got our push. We know that we're going to create a new node to store this data. So, in this case, that means that our temp data is going to equal what? What? D, right. Cool. Now, this is the interesting thing with the stack. When this temp variable, where are we going to put it? It's going to go on the top of our stack, right? What's currently on the top of our stack? Well, it doesn't, it's the top, whatever top points to, right? The top pointer currently points to the top of the stack, whether it's empty or not, right? So what we want to do is we want to say, hey, this new node is the top, and whatever the top used to be should be whatever's below it, right? So what we actually do here is we go temps next is going to equal what? Top, right? So we're going to point the new nodes next to the old top of the stack. Does that make sense? Are you with me or have I lost you? Okay. Then the next thing you have to do is you need top to point to what? Top keeps track of where the top of your stack is. Now that we've added this new node into the stack, where should top now point? Top should now equal the temp, right? So now we point top to the new top of the stack. Make sense? Guess what? That's it. That's how you actually push. It's pretty clean. You don't have to do any checks if it's empty, if it's not empty, do different stuff. Because you're always adding to the top, once you add something in new, you basically just make it, or it's next, the element that's next, or the element, you can think of next as being below if you want. So the element below the new one is going to be the old top, and now the new top is going to be the one we just added. Does that make sense? Okay, so let's actually try this out, right? Because that's what we want to do. So let's actually try this out here. So we want to add something or push something. Let's push strings. How about cheeseburger? Anyone have a cheeseburger for breakfast? You guys don't eat cheeseburgers for breakfast? Okay, I don't either. I just assumed. Pizza? Anyone have pizza for breakfast? How about we'll push a large coffee? Anyone have a large coffee for breakfast? So we just pushed 3 things on the stack, right? Cool. So we should see, let's see if this actually works, right? So now that we've pushed these 3 things on, these strings, let's see if it works. Compiles, runs, and it tells us even, hey look, delete should have been happening now. So what does that tell us? It tells us our stack actually contains data. But we have no idea what's in the stack, do we? So this is a problem. So what would actually help us here to figure out if our stack is working properly? Yeah, it would be good if we actually added here a toString function. So before I do pop, I'm going to add a toString function to make sure this is actually working. So so this is going to display the stack's contents as a string, top to bottom. Okay? Make sense? So the toString function is going to display the contents of the stack top to bottom. So it's going to return a string. We're going to do stack : toString. And we're going to return what we're going to. So we're going to actually, let's actually create a new string called. How do we want to do this? What do you want to call it? There's lots of ways we can do it. Just what do you want to call it? To return. Sure, you can call it that. I also could call it S. or result, yeah. So we're going to start out with some new result, right? Here's what I'm going to do. I'm going to set the result here to be, just so I remember this, to be top and an arrow. Okay? So I'm going to say this is the top pointer, right? Actually, even I'll put this in brackets so you know it's not real data. So the top is going to point to, and I'm going to say what element is at the top, and then I'm going to keep going all the way. Okay? And I'm going to return this result. Now, what do I want to do here? I'm going to want to do a loop, right? What about if it's empty? Well, actually, before I do this, wouldn't it be good if we had a function that determined if it's empty? That might also be useful, right? So I'm going to add another function called isEmpty, which is going to tell me if it's empty or not. Make sense? So I'm going to implement that down here, which is bool stack isEmpty. What's it going to return? It's going to return. It's going to be true if top equals what? No. So all I have to do for the isEmpty is just return top equals null, right? Make sense? Everybody with me? We totally could. Here's the thing though, we're going to want to know the isEmpty. We're going to use in our deconstructor later. I know we will. We're also probably going to use it in our pop, right? And so isEmpty is something we're going to do a fair bit. So it's a good helper function to check. Okay? This is going to be useful, so let's actually keep it. So now what I'm going to do is I'm going to do a thing here which I'm going to say if isEmpty, I'm going to actually make the result string equal to itself plus what? I'm just going to say a dot, okay? Just for empty. Nothing, okay? I could say null. Would you rather I said null? Would you guys prefer that? Yeah? Oh, because we implemented that in there isEmpty, right there. I'm using the isEmpty rather than just saying if top equals null because I know I'm going to use it a lot, and then I'm going to use it several times. And if somebody's looking at the code, because we've got a lot of pointers in it, if I see an expression if isEmpty, I don't have to think, okay, top equals null means it is empty, so that's what we're checking. Because that's an if statement. Top equals null is a Boolean expression. It says return true if top equals null, and it'll return false if top does not equal null. So we could have written, sorry, I didn't understand your question, but now I do. We could have written this as an if statement. If top equals null, return true, else return false. But this is actually a shorthand version of that. You can take what the expression, your if expression, the Boolean expression, and you can actually put that as the return, and it'll just return true or false, depending on how it evaluates. Okay? So, yeah.
So if you were trying to do like high performance software, if statement that calls isEmpty, that's like a whole other function.
It is. It could be, yeah. And this is one of those things where it's a trade-off. This means that we call a function, and then we check top equals null versus checking top equals null directly. Here's the trade-off is there's a difference here between performance and maintainability, right? This will actually make it more readable and probably more maintainable. Because also, this expression, if I actually change it later, then I only have to change it in one place here. But if I make some difference here where I modify the structure, you know what I'm saying?
Yeah.
So there's a trade-off here, and this is one of the things, as you become more experienced programmers, you'll actually learn about when to use the trade-off and when not to.
Does like plus have like a keyword like fast follows inline or something where it would like inline the function?
I actually would have to check that, but we can talk about that after. Okay. So this is basically all we're doing, right? Result equals result plus null, right? And then what do? We could return our result here if we want it, right? Now, let's just make sure this works. So if we actually call here s to string before we add anything, right? So we can now test this just for when we have an empty string, right? So if we actually do that and output, we can actually go g++ stack, compile, and what does it tell us? This is the output we get when it's empty. Top points to null. Okay? Now, that doesn't help us much for once we add data. So we need to also have an else branch here where we're going to actually go and we're going to actually have to print out what's going on here. So it turns out the way we need to do this is we actually need to create a pointer and move the pointer through the data for each element. So we're going to create a new node, which is just a temp one again, but I'm going to call it current. Okay? And I'm going to start current pointing to, what do you think? Where should current start? It's going to start by equaling top. That's right. And what I'm going to do is I'm going to say, while current does not equal null, I'm going to display out, or I'm going to set into my string, sorry. What was my string called? Result? I'm going to put into it what? Current data plus another arrow. Okay? Why? Make sense? Now I need to make current equal to what? To move it. I don't want to, see, because I don't want to ever mess up my top pointer. I want my top to always point to the top of my stack. So I can't move my top through the stack to check the variables, because if I change it, I'll lose, it's the only reference I have to the beginning. Okay? So I always keep top pointing to the beginning, and I create a current, and I move it through the list. Yeah? Yeah, so I make current equal current next. And I'm going to go doing this until it no longer equals null. And then at the end, I'm going to make result equal what? Result plus null. We could still do null because at the end it points to null, right? The next is null. Or we could just say, what? Could do bottom.
If we find that current is equal to null and then we break out of that while loop, we can just pass current next, like current data to it, because it wouldn't be null if we get out of the while loop properly.
It'd be 0 because null is like keyword.
So now I'm going to do this, and I'll just move my result up here. I could have done my result at the bottom of each of these down here, but by putting it here, it means it doesn't really make a difference, to be honest. So now let's actually see what happens. Let's take this, and we'll say output when not empty. Okay? And let's see what happens here. So what should we expect as the output? Will the output be cheeseburger, pizza, large coffee? Or will it be large coffee, pizza, cheeseburger? Right. Awesome. Oops, wrong file. Okay, here we go. Let's actually compile this. I love when things compile and run it. And what does it say? It says the top points to a large coffee, which was the last thing added, which points to a pizza, which points to a cheeseburger with a typo, which points to the end. It's done. And I'm going to fix cheeseburger here as well. What? Yes. So, does that make sense? Does anyone have a question about this? Is this freaking you out, or are you okay with it?
Kind of tough, not gonna lie. Let's go pop it.
Okay, so that's our push. Now, let's actually go about, so far we've done like all the functions except pop. And we also haven't done the delete. But here's the secret about the destructor. I'll tell you what my deconstructor solution is after. But let's actually now do pop. Okay, if we're going to pop something, what happens if it's empty? Yeah, I'm going to do something really ungraceful. I'm just going to exit if it's empty. Now, let's do so we're only going to be able to pop if it's not empty, right? So if not is empty, I'm going to pop. Make sense? Or maybe I'll just return empty as my string. I could do that. That's not really good, though. Anyway, we'll figure that out after. So let's do our if is empty. The first thing we're going to want to do is, what are we going to be returning here? What do we know we're going to return?
The data of the top.
We're going to if we want to pop something, we want to pop the top element, right?
Yeah.
So if we want to pop the top element, we're going to want to return string data, right?
Yeah.
So we can have a string here. Let's call it.
Value. I need the value.
I'll call it value for you, and then it's going to be, we're going to return top's data is what we want to return, right? So let's store the data that's in top into a string called value. Okay. Now, this is where the cleanup happens. If we pop something off the top of the stack, right, we need to now delete that node because we're no longer going to use it. And what do we have to do with the top pointer? We have to point it to whatever the old top's next is. So, what we're going to need to do, in order to be able to delete it, we're going to need to create a pointer. Let's call it old top, because that's a really... And we're going to make that equal to top. Okay? Now, that keeps track of where our old top was. Now what we're going to do is, what do we need to do with our top? What do we want to do? We want to move the top to point to what? Right. So we could say top equals top's next or old top's next, right? We can do old top. It doesn't really matter. So we now have a stack where we have the top item is old top. We have an old top, and we have the item right below it is top. Because we're popping that one, what do we need to do with that old top now that we've moved the top? We now have to delete it. So now we go delete old top, right? And then what do? Because we copied out the value that was in that old top first, right? That means when we deleted the node, we didn't delete the data too. We actually made a copy of the data and put it in our string value. So now that we've cleaned everything up, we can return that value. Okay? And now what I'm going to do is I'm going to do an else branch here to handle, I'm going to say, because you can't pop from an empty stack, I'm going to have a little message displayed here which says cout, you can't pop from an empty stack. And I'm just going to do exit. I'm just going to exit the program. Just terminate it. Okay? What? No. It'll work. Mm-hmm. Yeah. It should. Let's see. Yeah. So now, let's make sure this works. Well, first off, I want to make sure pop works if I do it right away when it's empty, don't I? So I'm going to do spop here before I ever do a push. So if I do this, what should happen in my program? What? It should exit, right? So if I compile this and I run it, it says you can't pop from an empty stack, and it exits before you even let you push anything. That's what I wanted, right? So that's cool. So we know that works. Now let's see if it works. If we go and if I do a pop right here before I output, what should my output of my program be now? What?
I just have a quick question. It says our exit isn't declared in scope. Do you know why?
Library.
Standard what? C standard.
Okay, so just one comment here. Depending on the compiler, you may also have to include, explicitly include, I should say, C standard lib here, right? As well. So, what happens here when we actually do push these two things and then pop it? We should pop whatever was on the top, and the top item was large coffee, right? So now we see that, in fact, this worked. Now, what would happen if we did 3 pops? If we did 3 pops after 3 pushes, it would say top is null, right? Which is exactly what we'd expect. Now, we have a couple minutes left. What's the one thing we forgot to do here? Deconstructor, right. Well, guess what? If top equals null, we have nothing to... I'm going to actually get rid of this message now, if that's okay. What happens when we pop something? What happens to the node when we pop it? Deletes it. And if we pop all the nodes, what happens to them? They all get deleted. What do we want our deconstructor to do? Delete all of them. So rather than implementing this from scratch, guess what we can do? We can just say, while not equal to, while not is empty, oh, typo, while not is empty, guess what we're going to do? Pop. And what's that going to do? If the list is already, if the stack is already empty, what's going to happen? Nothing. If it's got 1 item, it'll pop once. If it's got 2 items, it'll pop twice, and it'll delete them as it does it. And we don't care about what the value pop returns in this case because we're just deleting and cleaning it up. Make sense? What? The top pointer? The original top pointer? Oh, so here's the thing. What we're saying is delete this S pointer, right? But we're essentially just defining what delete means. By the deconstructor is how we're defining the delete. So for a stack, this will delete the stack pointer, but first it will go through the deconstructor and it will delete all of all of the elements.
So every time you call delete, it looks for a deconstructor?
Yes. Exactly. And what this will end up with is it will end up with top equal to null, which means that there's no pointers, there's no dynamic data that's been, or variables that are left. Yeah. So that's where I'm going to stop this one now. But this is just an example of how you can use pointers with classes to create a data structure. We've seen, in this case, a stack with a push, a pop, a constructor, deconstructor, and a couple of helper functions like a toString and an isEmpty.